sun. The ability to physically study the atomic structure of the solar wind can dramatically improve our understanding of the formation of the solar system. Scientists believe the bodies in our solar system grew from a solar nebula made of gases, dust, and ice about 4.6 billion years ago. The outer layer of the Sun today may be composed of the same elements and isotopes as when it was first created. What if we could precisely measure the abundances of the elements in our Sun? Could we better understand why Venus has a thick atmosphere and is hot enough to melt lead? Or why Earth's environment evolved to sustain life? That is the objective of the Genesis mission, to accurately measure the composition of our Sun, to answer questions about our solar system and our past. To do this, Genesis collected solar wind atoms, pieces of the Sun, and returned them to Earth to be analyzed in the most advanced laboratories available. For 26 months, Genesis orbited 1 million miles from Earth, absorbing atoms of every chemical element on specially designed high-purity collectors at a rate of 1.4 trillion per second. On September 8, 2004, the sample return capsule re-entered Earth's atmosphere, headed for Utah and a spectacular mid-air capture by a waiting helicopter. Sadly, the parachute did not deploy, and the capsule impacted the desert floor at almost 200 miles per hour. Due to the heroic efforts of the recovery team, 15,000 pieces of the shattered collector wafers were recovered, still containing the solar wind atoms. After careful cleaning to remove surface contamination, many of the recovered fragments have been allocated to eagerly awaiting investigators. Armed with the world's best mass spectrometers, they have started extracting and counting the solar wind atoms. To date, precise elemental and isotopic abundances have been determined for noble gases such as helium, neon, and argon, as well as iron and magnesium. These are being compared with known abundances for Earth, the Moon, Jupiter, and comet Wild 2. The list of results will grow for years to come, as this reservoir of solar matter is tapped to provide the first exact measurements of the composition of the Sun. During the past decade, scientists have determined that about 10% of stars in the Milky Way are similar to our Sun with orbiting planetary systems. The most recently selected Discovery mission focuses on these extrasolar or exoplanets beyond our solar system. New deep space observing techniques from the most powerful ground-based telescopes are allowing planet-seeking astronomers to detect giant planets the size of Jupiter and Saturn that orbit other stars in the Milky Way. The primary goal of Kepler is to search for Earth-sized planets around stars in our galactic neighborhood. Using the same technology found in consumer digital cameras to measure the intensity of light, the mission will look for indications that a planet is crossing in front of its star, called a transit. As the largest telescope launched beyond Earth orbit and with a vast field of view, Kepler expects to detect transits of thousands of planets, including hundreds in or near a star's habitable zone, that region where water may exist in liquid form, increasing the probability of life. Kepler's photometer will return data to offer insights into the evolution, structure, and diversity of planetary systems, as well as the characteristics of stars with terrestrial planets. The Kepler mission is a vital step in helping us answer one of the most enduring questions humans have asked throughout history. Are there others like us in the universe? NASA's Discovery missions are achieving groundbreaking science, demonstrating that small, high-quality missions can pay rich dividends while driving new technologies and capabilities with the potential to benefit billions of people on Earth. Discovery is venturing beyond the world we know, finding the unexpected and getting closer to the truth. Discovery is unlocking mysteries of our solar system